we had introduced in the last class the notion of what is known as time average, and also we mentioned what is known as ensemble average. So time average is something like as if you have a trajectory of a particle over time and you're calculating some quantity. It could be momentum, could be position, or could be anything, could be kinetic energy of. Okay. So basically you calculate that quantity along the trajectory and take an average of that quantity along the trajectory. So trajectory has to be quite long. So if I take, sorry, if I so this is my, so I have a trajectory of I'm using capital X, so just stick to capital X. Capital X is the quantity, some measurable quantity, which is a function of time, and I have the trajectory of this. It could be position, for example, of the particle. Okay, so I just integrate this over a time window starting from some initial time t0 and going to some final time t0 plus tau, and in such a way that tau is very large. So I divide it by tau and take the limit. Tau goes to, sorry, I have to write it properly. Your limit tau goes to infinity, and this I designate as x bar. Is this fine, this definition? Not very complicated. Okay, and if you just please tell me if it is fine, just tell me yes. Okay, should not be a problem. I hope
Yes,
this is
sir, we
fine.
get this.
Yeah, this is very simple. Yeah, and you can also alternatively you can define this as x, of course, your limit. There is nothing special about the initial time, so you can always think of that your initial time is time 0, and you go from 0 to tau 1 over tau xs ds. This s is smallest is the dummy variable for time t. I hope you understand. So this is the way a time average is defined. Similarly, I said that there is something called ensemble average. But before I define ensemble average, I should define what we mean by ensemble. And before we define ensemble, I have to define quantities like microstates and macrostates. We'll do that in a minute. But let me write down the ensemble average. And this is for the same quantity, it is written using this angular bracket. X of within an angular bracket means the ensemble average of x. And this is given by a sum over of this. I just multiply your xi with some probability pi, this is ensemble probability density, and divided by total number of ensemble elements in the ensemble, rather in ensemble, and you sum over this, and this number of elements in the ensemble should be very large. Okay, and the first postulate of statistical mechanics is as follows. Is if I take a time average over a sufficiently long time, then that time average should be equal to ensemble average, provided I construct an ensemble with number of elements very large. Okay, so this is called the first postulate of statistical mechanics. It will be clearer because I'll explain things, because I have not properly defined ensemble, which I'll do today. Okay, So it tells you time average is equal to the ensemble average. How many of you knew about it?
Sir, I knew it.
Who is
Nashit.
this? Okay.
Nashit.
Okay. How did you know that?
Sir, this is the ergodic hypothesis.
It's a
Yes.
consequence of it is the consequence of ergodic hypothesis actually.
Yeah.
Yes. Yeah, you're right. You're right. They're very. You're also loosely you can call it ergodic hypothesis. Yes. We'll talk about it later. Anyway, but in order to explain ensemble average, first let me explain few things. One is what do you mean by macro state of a system. So in order to define a macro state of a system, let me give you an example. So in this room, I have these gas molecules. No, nitrogen, oxygen, all these gas molecules are there. So there are many in numbers, billions of gas molecules. Okay, each of them are having position and momentum, and these positions and momenta are changing as a function of time because these particles are moving around. Okay, but I know the temperature of this room is, say, for example, 24 degrees C. The temperature is constant. Okay, and if I have a room which is closed room, then the gas molecule cannot come in, cannot go out. Then the number of gas molecule is also constant. Okay, and if you have very hard wall, then the pressure inside this room is also constant. So I can define the macro state of this system, which is a gas molecule in a room or in a box, by three variables. For example, number of gas molecules, pressure, and temperature. Okay, is this clear? Okay, so entry is with only LDAP. So I can write, I can use a notation M. M not is not for mass, is for M stands for macro state. So macro state is defined by some state variables, some variables such as pressure, number of molecules, temperatures. Okay, these are state variables. Is this clear? At least you say yes, so that
Yes,
I
sir.
know. Yeah. Now, what is this? Well, this system, I told you, the system is a box or a room filled with gas molecules. So think of a think of a cubic box, any box of volume V, and temperature is T, and the pressure is P. Okay, and the number of particles is also constant N, like this. Okay, and I can define that. Okay, I have these gas molecules here. Now think of, forget about the volume. So I'm not considering volume for the time being. I'm saying the pressure is constant. Doesn't matter. Okay. Okay. Now for this particular macro state, I know there should be there should be a micro state. What is micro state? I told you in the last class that micro state, if I am following a classical mechanical description, it is coordinate. It is the position and the momentum coordinate, isn't it?
Yes, sir.
Of all the constituents. Of okay. So how many particles are there? N number of molecules or particles. So actually there will be 3n position and 3n momenta coordinates, isn't it?
Yes, sir.
So total 6n. And if I have 1 mole of gas in a box, then it is huge number. So it is like 10 to the power of 24 number of coordinates you have here, isn't it? Okay, huge. And this is called your phase space. I told you in the last class. Okay, this is called phase phase. So phase phase is nothing but your the 16-dimensional space. Now think physically what is going to happen. Now at a instant of time, I have this n number of molecules, each would have a particular value of a position. Each would have a position coordinates and momenta coordinates, but this is at some instant of time. As the time progresses, these things are also going to change. So your phase coordinates are also going to change. So as a result, actually ideally I should have plotted this in 16 dimension, which is not possible. No. What I can do, I can collectively plot them, at least mentally, or like this, that I have a collective momentum coordinates and some collective position coordinate, and some instant of time, a point in this coordinate space, this point shown here, is the phase of that system at that time. And what will happen? So as the time progresses, this point will change, isn't it? It will evolve in the phase space. So, and you'll have a trajectory in the phase space. And this is called phase trajectory. And what is important here is that for one macro state, I can have one micro state, of course, but I can have another macro state, the same macro state, another copy of that macro state, another copy mentally I can think of. M stands for macro state. That would correspond to another micro state. And these two macro states have no difference. They are same. Essentially, they are mental copies. So I can have n number of, not n, rather m number of macro states, mental copies of micro states. And as a result, we'll have also nm number of microstate. If I say, okay, for each copy I have one microstate. Okay. Now rather than using nm, I use this notation nm, like this curly n, capital N, and this is actually number of microstates. And this number is very large. What I am saying that I can have many microstates which will correspond to a particular macro state. The macro state is defined by this state variable, say number of molecules, pressure, and temperature. With same number of molecules, pressure, and temperature, I can have mental copies of this, which they are identical macroscopically. They are macro states, but microscopically they are different because they have different microstates. You should get this thing very clear that many microstates can give rise to the same macro state. It is not one-to-one correspondence. It is like one-to-many correspondence. Is this clear? Because as the time progresses in this room, I have gas molecules, their position and momentum is changing. So their microstates are changing. But since this is a closed system, the number of molecules is conserved, pressure and temperature, they are also unchanged. So the macro state does not change. You go from one mental copy to another mental copy of the macro state you can think of, but the macro state remains the same, but your microscopic states that change.
So I
Isn't it?
have one question.
Yes.
So now here curly n is equal to n sub m. Is that
Yeah,
correct?
I just use this curly n. Yeah, same. So you see that I'll be using n different times, but usually this n is very large. Okay. So early n is the number of microstates. Okay. Is this clear? And this is usually, it is expected that it is huge in number, isn't it? In principle, it is infinity. You understand? Because there is
Yes,
an
sir.
infinite way of having this. May not be infinity, but very huge. Actually, n, this curly n goes to infinity. That is the limit. And so all these microstate can give rise to the same macrostate. So now these mental copies of huge number of macrostates is called an ensemble. So I can think of an ensemble that where each element or each member of the ensemble has the same, are in the same macro state. For example, this, but there are many copies of that. These are mental copies. And how many are there? There are n such macro states. Now, don't be very particular about this curly n. If your number of molecules is very large, your number of macro states are all number of mental copies of macro states are also going to be large, because your number of micro states are also very large. So the idea is as follows, that each micro state can correspond to a macro state. Okay, but I can have different microstates. They correspond to the same macro state, but I just distinguish them by saying that they are same, but they are just like mental copies of the same thing. I'm just making mental copies of that. Okay, so this is called ensemble. So ensemble is a collection, huge collection of mental copies of systems that are in same macro state. Is this clear?
So I had one question.
Yes.
So are the microstates same in this case, or are they different?
Now the question, they are, for example, in this case, I can think of that each correspond to a microstate, and this microstate, it is expected that they are different. But you can also have a situation that you encounter the same microstate. So it is not very important, because number is so huge that the number of possible microstates is huge. For example, if 95% of them is not a repetition, maybe 5% could be a repetition. Doesn't really matter, because n, this curly n is huge. So just think of mental, this is a little abstract concept, because you can think that these molecules are moving around, the position and momentum is changing, but keeping the same macro state. It is possible that, okay, it will come back to same micro state, isn't it? By accident. It can there is a possibility, but that possibility is very less. You understand, Muskan?
Yes, sir. Convinced. Okay.
Yeah, so that is not a very important thing, but what is important is that there are many possible microstate that can give rise to same macrostate, and your system is following classical mechanics, so that you describe your system by set of position and momenta coordinates. Clear?
Yes,
This is
sir.
very important. So I'm not sure whether this is the way it is taught in 408. I'm not sure, but this is the way it should be taught in statistical mechanics. Okay, so get this thing very right. Any question? I'll proceed. So this ensemble concept was introduced by Gibbs, the gentleman's picture I showed in the first class. Famous engineer come physical chemist from US. He was the first one to get a PhD degree in engineering in the US, I think. Okay, so if you have ensemble, then it is possible that, okay, I have a density which I'm calling ensemble density. I can always define. Now, this ensemble density is obvious that it depends on the microstates of the system. It will depend on yes, all, I think I should, all momenta coordinates. So P bar means all momenta coordinates, like n particles are there. I'll tell you what is that, and Q bar. Okay. This ensemble density depends on all the momenta and all the position coordinates. So P bar means all, like P1, P2, P3, like this. Okay, and Q bar means all, Q1, Q2, for n particles. Like if each particle can go in 3 dimension, there are like 3n. So P bar means 3n momentum coordinate, 3n momenta coordinates. Three n position. Okay. So what is this density, ensemble density? Just let me write down again. This is rho, huh? Rho PQ. Now I have this graph. This is your all P and Q, which is like your P alpha, rather Q alpha. You can write it like this. It's better. And I have a point in phase space at some instant of time. Okay. Is this clear? Now,
Yes.
now I can think of a very tiny volume element around that point, in the neighborhood of that point, a tiny volume element. Okay. And this volume element is is called d gamma, and this is called the tiny, this is the tiny volume element. What is this? This is nothing but your d3 pi, d3 qi, I from 1 to n. Is this clear? If I write like this, is the product of
Yes.
all dp and dqi in all the direction, isn't it? Like you have like 6n such possibilities, like 3n p coordinates and 3n q coordinates. So that the tiny volume is given by this, the product of such small volume element in all the directions. Okay, in 6n directions, like in 6n direction, but it's in volume, so it is, there are n such product. Okay, is it clear? It's not a difficult thing to do.
Yes,
If I
sir.
have two particles, then I'll have only like two such thing. Like I goes from 1 to 2. N is the number of particles here. This n is not the Carlian, but number of particles. But in all the cases, these n's are usually very large. Okay, so uh, so within that volume, I can think that within this volume, this d tau volume, there are d capital, this Carlian number of microstates. Okay, so dn number of d curly n number of microstates. Okay, so it is obvious that this density, ensemble density, will be proportional to the number of points in this tiny volume element, which is the number of microstates, divided by total number of microstate. And also I should divide it by, because as the volume increases, it should also depend on the volume of this this tiny volume. So I should also divide by the tiny volume. Okay, and this is not complete. Of course, I have to take a limit in order to define a proper density, that your number of microstate is very large. Okay. People I'm teaching and they're okay. Somebody asking me that she cannot join. Anyway, so this is the definition. Okay, is this fine with you?
Why are we divided by capital N with capital curly N?
Of course, because it is a density, no? Okay, so you have to have something which is dimensionless in a way. And in other way, you can say that if I take this density has to be constant. So if I multiply with this time, then integrate of this over all possible values of tau, gamma, what I'm going to get? I'm going to get, what is this?
Unity.
Yes. So your probability is conserved. So basically your density is like a probability which is conserved. Of course, you have to divide by the total number of microstates, because the density, that should depend on how many particles you have, and you have to divide it by how many. What is density? Density is mass divided by unit volume, isn't it? So it is like that. So dn divided by this capital N times d tau, and this is how this this is the volume of the box. So this is how your density in the vicinity of that point is defined. Okay. So what is the density of having this within the vicinity of that point when you change your momentum position from P to P plus dP and Q to Q plus dQ is given by this fraction. Because as this volume element increases, so size of the volume element, this thing should also change, isn't it? So that's why it should be divided by the capital N, the total number of microstates. So this is how it's defined. Any distribution, any density is defined like this. It is the dn is the number of points within this volume element divided by the total number of points available, and also divided by the volume of that tiny area or the tiny space. That will give you a broad density. So what I need to know now, that okay, then this is called probability density function, and I would like to know how this probability density function evolve in time. How does this probability density function evolve in time? That is a $1 million question. Okay. And this density is also called the ensemble density or ensemble distribution. So now how can I define ensemble average? So I take any quantity, say O, any quantity that depends on momenta and position coordinates. Then the average, this average is ensemble average. Ensemble average of this is given by what? Is, can you tell me what will be the definition? You have to take this guy, multiply this with your, of course it also depends on time in general, and then integrate over all possible position and momentum coordinate, and this gives you the ensemble average. So this is just like average. For example, if I take an average of x, how do I do? In general, I do this, isn't it? Similarly, when I'm taking an ensemble average of a quantity, ensemble average of this quantity, then this is given by this expression. Is this clear? This definition of ensemble average. And see that this density, I did not write it explicitly, but actually the density depends on time. It depends on time. In general, okay, in general it depends on time. Any question?
So, sir, this is a definition of the ensemble average of the quantity O
Yes.
using the density function.
And
And at the start of this lecture, we started with a definition which went like limit n tending to infinity 1 over n,
yes,
sum
yes.
over I, pi, xi.
Yeah.
Uh,
So yeah, of course, because yeah, this is how. Yeah, that definition was a discrete version of it. This is, I'm just going to in the continuum description. Okay, this is a continuum description. When
they are
n goes,
essentially
yeah,
equivalent.
yes, they're equivalent. We'll connect that. Okay, now next question is, how does this density change as a function of time? And what do you mean by equilibrium also? And this time evolution of this quantity is given by what is known as Liouville's theorem. Liouville's theorem. How many of you know? How many of you heard about Liouville's theorem?
Sir, this is in my MSc course. So,
Who is this? Ramanand.
yeah, sir, this is the MSc course.
Only know you know the name.
No, derivation and all the things. That density with time evolution of density with that is going to conserve.
Okay, we'll see. Now you mute yourself. Yeah.
Okay.
So I have a point here. In this is my Q alpha versus P alpha plot. I just take in one dimension. Okay, take one degrees of freedom, and this value is your Q alpha value. This value is your P alpha value, and I can think of volume or the area around this, and of course this is your dq alpha, and this is your dp alpha. Is this clear?
Yes, sir.
Okay. Now this is at time t. Then I wait for some other time. I go from time t to t plus dt. So this whole thing will evolve as a function of time, isn't it? And maybe after some time, this point has now moved here. the central point here. Okay. And then I can think of another volume element around this point. But you will see that this volume element is going to be distorted. And this distortion is given by this. This is dq alpha prime, and this is dp alpha prime. Why it is distorted? Because you see that velocities that depend on the position, isn't it? So the points shown here, the corner points, they have different values of, slightly different values of p alpha and q alpha, isn't it? So as a result, all these points, the derivative of this point with respect to time will have different values. So they will have different velocities. As a result, all these points will move with a different velocity. So after some instant of time, if I follow this particle, this corner point, these corner points have now moved not equally. Okay, they have moved differently. As a result, now the volume element around this central point is now distorted. So we have a distorted volume element. So we had a volume element d tau at time t, which is this, and now I have a volume element d tau prime at time t plus dt. Of course, this is going to be distorted. We'll come to that in a minute. Now, what is can I write down this q alpha prime? Now, q alpha prime is this. And this is p alpha prime. Okay. So you have q alpha prime, and then you have q alpha prime, and then you have p alpha prime. Now, can anyone tell me what is q alpha prime? What should be the q alpha prime?
You mean Q alpha plus some change?
It should be your initial q alpha plus q alpha dot into dt, isn't it? Plus other higher order correction, which I am not taking. Is this fine?
Yes, sir.
Similarly, what will be p alpha prime? P alpha?
Alpha plus P alpha dot dt.
P alpha dot dt plus higher. Now, these higher order corrections are very tiny. I can neglect this actually. Okay. Like almost 0. Okay. So what is important that I have these two equations. Is this fine? If you
Yes,
have any,
sir.
this is not
Yes,
very difficult. It's very easy. So, but similarly, I can write what will be this dq alpha prime. Can anyone tell me? If you can tell me, then your life becomes so easy, and half of the problem is solved.
dq alpha prime is equal to dq alpha itself.
Yeah. Then they are not same, because each corners are moving with different velocities. They don't have the same distance. It has changed. Kailash, you understand?
Yes, sir.
So what will be the correction?
Plus dq alpha dot dt. That's correct.
What about what else? So actually, you'll have correction like dq alpha dot divided by q alpha into dq alpha into dt plus higher order, which I am not taking. Is this clear? This has to be clear. What is this? This is derivative of the velocity with respect to the separation. Separation multiplied by separation. Is this clear? This is very important because your initial dq alpha plus the velocity with which dq alpha is going, but you take a derivative of with respect to the separation, then multiplied by the separation and the distance traveled dt. This is how it should be. This is how it should be. Similarly, what will happen to dp alpha prime? Anish, what will happen to dp alpha prime?
dp alpha plus del.
Here also you have a velocity, but velocity means it's a velocity with off the momentum.
Yes.
Change of momentum, yes, of course. It will be something like clear? Is it clear?
Could you explain once again why we did
Yeah.
dq alpha and then multiplied it by dq alpha?
Okay, so if I see the change in dq alpha is because of what? It is because of change in q alpha as well as because of change in dt. Now, because of change in time, there is a change in dq alpha. You understand what I'm saying?
Yes.
It is like that. So first of all, you do dq alpha. So this is the velocity of that tiny differential, the velocity of that, and you take a derivative of that over which this velocity is changing, and then you multiply it by the separation and also multiplied by that tiny time element, because this is the way you do in calculus, isn't it? Because this is your final dq alpha, which is your initial dq alpha plus a correction, and this correction is because why these things are changing, because these things are moving with different velocities. So there has to be a velocity, isn't it? Okay, and this velocity, yes, there has to be velocities, but and see these so velocities, for example, these corner points, no. So basically that depends on what is the magnitude of dq alpha, isn't it? This magnitude of dq alpha. So if I had chosen a slightly bigger volume element, I would have a different answer, isn't it? So it should also depend on the magnitude of dq alpha. So as a result, I have to take a derivative of this dq alpha with respect to time divided by the magnitude of this. Since I divide by magnitude of this, I have to multiply it also with this and also multiply it with dt. Thing dimensional wise, same, because it is like dq alpha. So as if you have dq alpha is in the numerator, also in the denominator, also in the numerator. dt is also in the numerator, denominator, and also in the numerator. It's not like that, but you can think of like this. But it is dimensionally correct also. But physically, it basically means that my endpoints are moving with different velocities. So in order to see what happens to this element dq alpha at time t and time t plus d tau, you see that dq alpha has changed because my endpoints have moved with different velocities. So this is a change in velocities, but also depends on how much they are separated. So you have to divide by that separation. Since you're dividing, you have to multiply it with also the separation, and also it depends on how much time we wait. So you have to multiply this also with dt. This is the standard calculus thing, you know, multivariable calculus.
Got it.
If I have a function of x, which is x is also a function of t, then f dot, you know how to write that. F dot is del f del x into del x del t, isn't it? It is like that. It is like that. Okay. So now I have this new dq alpha prime and dp alpha prime. Now what was the initial volume element? It was like this. And the final volume element is now what is d gamma prime? Can anyone tell me? I have to multiply these two. So I'll have a term like dp alpha dq alpha, that is common. I can take this common. I'll have 1 plus I'll have term like dt square, which I'll neglect because it is higher order in t. I don't want to take it. So I'll just take only the term which multiplies this with this and this with this. And then I'll take dq alpha, dp alpha common. So I'll have two terms. What are the terms? These terms are going to be dq alpha dot dq alpha plus dp alpha dot dp alpha dt. Of course, I have higher other terms which I neglect. So what I have here is this. Is this clear? Now this is my new volume element, tiny volume element, which is dp alpha dq alpha to this. So I'll go to the next slide. I'll write down again. So what I have here is d gamma prime is dp alpha dq alpha into 1 plus, tell me what is there? You can have a look. dq alpha dot by dq alpha plus dp alpha dot divided by dp alpha. Is this clear?
Yes, sir. Well, we have equation relating P alpha
Now,
dot and P alpha.
now we'll go back to your classical mechanics. We'll go to Hamilton equation of motion. What is the Hamilton equation of motion? I tell you, if I take the partial derivative of Hamiltonian with respect to the momentum, what I should get? I should get q alpha dot. And if I take with respect to q alpha, what should I get? This is fine. Remember this. Check your notes. I hope people are following.
Yes, sir.
Yeah. So now I can make use of this here. If I make use of this, what I'm going to get? I'm going to get d gamma prime equals to d gamma into 1 plus, what is this? D dq alpha of q alpha. Q alpha dot is this. So the first one is d2h dq alpha dp alpha. What is the next one? Next one, a minus sign will come. So it will be
H.
d2h dp alpha dq alpha. And the order of differentiation is not important. So what is going to happen? In other words, phase volume is conserved.
So there is a dt factor, right?
Yes, I did not write that. Okay. But this is fine, no? Phase volume is conserved under the Hamiltonian dynamics. Is this clear? How many of you know that? Know about it? Tell me. Ramanand?
I am not going to derivation only there. We assume that both volume is not going to change. Means initially we consider without any derivation.
Okay, okay, yeah. Mute yourself, yes.
Okay.
So phase volume is conserved under Hamiltonian dynamics. Okay. This is very important. So if my particles are following Newton's equation or Hamilton equation of motion, then the phase volume is conserved. Any physical significance of that? Can you relate to something? There are people from engineering, mechanical engineering.
Yes, sir.
What does it mean? If the phase volume does not change with time, what does it mean? Like, strictly speaking, I should have written like this, no, because it should be something like your alpha dphi alpha dq alpha is in all dimensions. I did it in 1D. Okay. But have you encountered this elsewhere? A phase volume is conserved. What does it mean?
I think so if we relate by fluid mechanics, so the
Yeah.
density is like the material derivative of the density with respect to time is like zero, something like that.
So it basically means,
Incompressible.
yes, yeah, density does not change. And it is behaving like what is known as incompressible fluid. Isn't it? In other words, if I take a divergence of this velocity field is zero. So what is happening? My volume element is changing its shape, but the volume does not change. So the volume element can change its shape, but the volume remains constant, which basically means your phase density, the phase points, they behave like an incompressible fluid. Since you guys do not know much about fluid dynamics, I'll not go into detail, but it basically means the divergence of the velocity field is zero. It will do something like that. So what, in other words, what can I do? Tell me.
So does this mean ensemble density is constant in time?
No, that doesn't mean. It basically means this. It basically means if I define a density like p prime q prime at t plus dt, this is just equal to the density at p, q, and t. I have to change everything. I change time, I change momentum and position, then the density is unchanged. This is the characteristic of an incompressible fluid, and your phase density also behave like the density of an incompressible fluid. Okay, so this is the definition. Okay, is this clear? So
Got it.
maybe I'll do it little more. It will be clear. Sorry, this should be p prime and q prime. Sorry. And what is this? This rho p prime q prime I should have here actually, comma t plus dt. Just use this. times my, yes, okay. Just wait for a minute. Your rho p prime q prime plus t plus dt. What is this? This is, in other word, it is p plus, oh, sorry, let's change. Yes. Now I can write it like this. What is this? This is nothing but, I hope you'll be able to follow this. Sum over all the elements of course, but then you also have the total this partial derivative of this with respect to t and then dt. This is fine if I write this way. This is fine
Yes, sir.
because I remember, because just recall. What do you recall? You have to recall a little bit of your calculus. That okay, that if I have a function, any function which is a function of say p, q, and t, if I take a total derivative of that function, it's called total derivative of that function. Is given by the partial derivative of that function with respect to time. Is a partial derivative, and then what? Then because of the change in p and q, there will be change time evolution of this function, and this is, we are going to write it like this. You will write that df d rho, sorry, the t p alpha into p alpha dot plus, this is actually p alpha dot, huh? Plus df dq alpha into q alpha dot. Okay, and this one is 0 if there is no explicit time dependence. But I told you that since this is incompressible fluid, this one equals to this one means d rho dt is 0. Okay, like incompressible fluid. Okay, so if your total derivative, this is also called the streamline derivative. The streamline derivative is 0. This basically means if I change my momentum position and wait for some time t, then my density does not change, which basically means my total time derivative of my density by changing the time as well as changing momentum and position, which basically means I move along with the flow, move with the stream. I move with the stream and see the change in the density as I change my position and momentum as well as time. That is 0. for incompressible fluid, because my phase volume does not change. Because phase volume is what? Phase volume does not change means that that density is invariant. Okay, so this is like incompressible fluid. So if it is incompressible fluid, then the total time derivative is 0. What does it mean? The total time derivative is 0 means I take this minus this divided by dt, that is your total time derivative, which basically means this whole quantity is equal to 0. Or in other words, del rho del t plus so this is 0, and this is a very important finding. Any question you ask me? Any question you ask me? Because I go back here, I show you the definition of your rho. Rho is given by dn by n. This is of course a constant, and if your d tau does not change with time, then your does not change with, it remains the same. So basically your density will be invariant. If I change my position momentum and wait for some time, I move along with the flow, then my density, I should not see any change in the density for phase density, and as a result my total time derivative, this total time derivative is what is actually, you can call from here, you can calculate, it is nothing but your rho p prime q prime t plus dt minus rho p q t whole divided by dt, which basically means this quantity, isn't it? Anish, Ramanand, Pooja.
Yes, sir.
Yeah. So as a result, this is a very important finding in this class. Maybe now what I'm going to do, I'm going to now make it even simpler. Okay. Now what I have here is this. So the partial time derivative of this density plus sorry, yeah, I can. So let us define something like this quantity within this curly bracket, and this is called Poisson bracket. How many of you know?
Yeah, I have heard.
And this Poisson bracket is defined like this. This is del L, del A, del Q alpha, del B, del P alpha minus del B, del P alpha. Sorry, del Q alpha has to be. Okay. So if I follow this definition of Poisson bracket, then what is this quantity? Again, in order to define this quantity, remember what is P alpha dot? P alpha dot is, remember this?
Del
What is,
H minus del H del Q alpha.
what is Q alpha dot?
Del H del P alpha.
So what I have here is the first equation, del rho del T. P alpha dot is like minus del H del Q alpha, isn't it? Minus del H del Q alpha. So I can write it like that, del rho del P alpha to minus del H del Q alpha plus del rho del Q alpha into del H del P alpha. What is this? This is minus, so this will come, I can just put this thing here. If I put this, what is this quantity? Hold this quantity. It is nothing but the Poisson bracket of rho with H. Is it clear?
Yes, sir.
Yes, sir.
Rho with H. So in other words, my equation becomes del rho del T plus Poisson bracket of rho with H is equal to 0, or del rho del T is equal to minus of Poisson bracket of rho comma H, which is H comma rho. That is not difficult to understand, no? The sign change. So in other words, del rho del T is the Poisson bracket of H with rho. And this is known as Liouville's equation or Liouville's theorem. Okay. You have to do little bit of practice. Okay. So the partial derivative of that density rho with time is given by the Poisson bracket of the Hamiltonian with rho. Any question so far?
I have a doubt from one of the steps in the derivation. There
Yes.
was one point where we had related the two volume elements.
Yes.
Can you please go over to that slide?
Yes.
Yes, so here we simply related the two volume elements by saying that just like d tau was equal to dq alpha dp alpha, we wrote that d tau alpha d gamma alpha is equal to dq alpha dp alpha both primes. So here we change the coordinates, but shouldn't we also calculate the Jacobian and
Yeah. Jacobian is
factor of the
Jacobian is
determinant?
unity actually here.
Okay,
Jacobian is unity.
not able to see how. Could you?
Yeah. It is. It is unity actually. See, you don't need to calculate Jacobian. Don't make things it's very simple, because Jacobian you calculate when you go from one coordinate system to other coordinate system. Here you are not changing the coordinate system. You're in the same coordinate system. Only you are looking at the time evolution. Jacobian, when you go from say Cartesian to say polar coordinates.
Polar.
Yeah, here you are in the same coordinate system. So Jacobian has to be unity, no? All the derivatives are unity. You understand? Because you're in the same coordinate system. Why would a Jacobian, you had a Jacobian? If you're changing the coordinate system, then only you need a Jacobian, isn't it? You go from x, y, z to r theta phi, or whatever, some other coordinate system, any other coordinate system, then only you have a Jacobian. But if you're in the same coordinate system, but you're looking at the time evolution of that point, the point has evolved, the point has changed. isn't it? This position and moment has changed.
Yes. Yeah, I get it.
So as simple as that.
Like that.
Yeah, don't make
Yes,
your
sir.
life make your life complicated. Okay, it is as simple as that. Okay. So, but this is called Liouville's theorem or equation. Okay. Now, next thing is, what do you mean by equilibrium in this context? In this perspective, what is equilibrium in this perspective? Okay, now what I have here, I have this. Just look at this. Now I say, okay, now if I assume that your density is a function of your Hamiltonian, if the phase density is a function of your Hamiltonian, if it's a function of the Hamiltonian, then what happens?
Only of the Hamiltonian.
To begin with, only of the Hamiltonian. Okay, so let us see what happens. Now, if you want to calculate this quantity, okay, this quantity, say rho comma h or whatever, h comma rho, doesn't matter, which basically means how should I proceed? You remember the definition of Poisson bracket, isn't it? You remember the definition of Poisson bracket?
That is
Yes,
sum over.
Yeah. So sum over whatever, sum over alpha.
Yes.
So the first term will be, actually it should be del. If I write rho comma h comma rho also you can do. It should be rho d rho divided by what? dq alpha.
PQ alpha.
But actually you should write this as dh into dh dq alpha into dh del h del p alpha. Got it? Minus the second term will be again you got it or not? And I can call this as
Yes.
p prime, because your h also depends on q and p. So what is going to happen to this quantity? Tell me. This is 0,
0.
because this is nothing but your p prime, isn't it? Okay.
Yes.
So if your p comma h or h comma p, the Poisson bracket is 0, your del rho del t is 0, which basically means rho has no explicit time dependence. You got it?
Yes, sir.
Yes, sir.
What basically means? Now remember, you had defined a average like this. Sorry. Okay. Now the time dependence of this average would come from the time dependence of the distribution, isn't it? Density. If your time distribution or the time, sorry, if your density is time independent, this is going to be time independent average, isn't it? So all the microscopic, if rho has no time dependence and it is a function of age. Yeah, okay? There will be this, any average quantity like O will be time independent. And what does it mean? It basically means any macroscopic quantity. If I take an ensemble average of anything like ensemble average of pressure or any other quantity I calculate, it will be time independent. What does it mean? Or the kinetic energy, what does it mean? It basically means your system is in equilibrium, and this is the definition of equilibrium. So your density is a function of age. If your density is a function of your Hamiltonian, then it ensures equilibrium, because then your density would not have any explicit time dependence, and all the ensembled average quantities would have no time dependence. Okay, so if I calculate average pressure now or after 5 minutes or after 10 minutes, after 5 nanoseconds, it's not going to change. And this is your equilibrium statistical mechanics. And that is how in equilibrium statistical mechanics your averages are defined. Is this clear? Any question, any queries? Tell me.
Sir, I have one question.
Yes.
Which is, so if the system is far from equilibrium
Yes.
or not at equilibrium,
Yes.
then one of the steps that we made in this derivation will have to change.
No.
Or will the entire
No.
process itself be different?
No. Why? Why? Because the fast derivation will not, because if your system follows Hamiltonian dynamics, then you're fine. The last step we cannot do. See, this up to this is fine if you're in equilibrium, of course. If you are in truly non-equilibrium, then the Liouville's theorem will change, of course, definitely will change. But that I'm not going into detail.
Okay.
But if you are close to equilibrium or in equilibrium, you have this Liouville's theorem, because the notion of ensemble is, strictly speaking, is in equilibrium notion, equilibrium concept. Non-equilibrium, we'll talk about it later. Actually, I'm just keeping that part now for the time being. So your equilibrium distribution is any distribution density which is a function of age. Okay, is this clear? But I can have a situation that I have a sometimes, yeah, somebody asked me whether it is only a function of age. So age is a constant of motion in this case. You understand, no? That I showed you in the first class, no? That Hamiltonian is a constant of motion because the time derivative of the Hamiltonian, total time derivative of the Hamiltonian is 0 if Hamiltonian does not have any explicit time dependence. That is done in the last class.
Yes, sir.
Yes, sir.
Okay, that is done in the last class. So okay, yeah, now I think I'll have 10 more minutes today. Just yeah, but I can have a situation like that. Okay, not only Hamiltonian, I have a system for which, say, I have angular momentum is also conserved, constant of motion. Say for a system I can think of, okay, In that case, what will happen? That the total time derivative of this is going to be what? Is going to be 0,
0.
isn't it? It is 0. And if it is 0, then also it tells you that, okay, that if I take Poisson bracket of this is del L del P alpha into P alpha dot plus del L into del Q alpha into Q alpha dot. Okay, and this is going to be, again, we are following Hamiltonian mechanics, so this is going to be del L del P alpha to minus del H del Q alpha plus del L del Q alpha del H del P alpha, and also you see that this is going to be 0 also. Okay, so in other words, that this L comma H is 0, the Poisson bracket is 0. This is a special case I'm talking about. Okay, this is a special case. It's going to be 0, and then I can define another equilibrium distribution that is a function of H, not only H, also is a function of L, total angular momentum. Okay, H is a function of PQ, L is a function of PQ. Then what will happen? Then if I calculate this P equilibrium with respect to H, what I'm going to get? That you can also show that it is also going to be 0, because I'll have like this P1 prime, where I take derivative with respect to Hamiltonian, plus P2 prime, where I take derivative with respect to, what is that called, the second argument, and this is going to be 0. So it can also be a function of some other quantity which is a constant of motion. But the minimum criteria is that your function, that distribution function, in order to be in equilibrium, has to be a function of your Hamiltonian. And we'll stop here. I think it's too much, because if I go further, I think I cannot start a new topic. But we'll stop here today.
So the second Poisson bracket is L comma H, is it?
Yeah, I should be L comma H, yes. Yes, you're right. Let me do it. It should be L comma H. Okay, so any question? Please ask me a question. You have 5 minutes. Yes.
Hello, sir.
Yes.
Yeah, what is the physical meaning to here? The probability density should have to be function of Hamiltonian. I'm not getting that point. Actually, if you think about probability density, so this is nothing but the number distribution. So how it can be related to the Hamiltonian?
Okay, that's okay. Let me maybe then spend 1 more minute. Okay. I want to do it in the next class, but for example, maybe I'll not do it here, but yeah, I'll do it here now. See, consider a case where you have an isolated system. Energy is conserved. Okay, energy is E. And this is, and you can construct an ensemble in this case. This is called microcanonical ensemble, which we'll discuss later. And what is the distribution for microcanonical ensemble? Can anyone tell me the Pearl distribution? Actually, it is a Dirac delta function, because your Hamiltonian is equal to the total energy. So you have a hyperspace like this, where your energy is equal to the Hamiltonian hypersurface. Okay, and this is a distribution function. This is a function of H, isn't it? And this is the equilibrium distribution in microcanonical flow distribution. What about canonical? Many of you have taken the course CH408. What is canonical ensemble? Here it is for a closed system, isn't it? And you remember that for canonical ensemble, you get what is known as Boltzmann distribution. How many of you remember?
Yes, sir.
And what is Boltzmann distribution? It is also function of H, because it is exponential of beta H. You remember this? That beta is 1 over kBt. This is a function of Hamiltonian. So that's why the distribution is an equilibrium distribution. Is this clear, Ramanan?
Okay. Yes, sir. This is
Yeah, yeah. With that, I think I'll stop today. Yes, any question? Somebody has a question? Any question?
Hello.
Yes.
Yeah. Sir, just a general question. So, sir, we were talking about near equilibrium, far equilibrium, these all things, a bit of it. So, what does it actually physically mean? How can we say that something is in near equilibrium or in
So,
equilibrium?
if it is near equilibrium, there is something called linear response. It is in the linear response regime. So, we'll talk about it after mid-sem. It's a very vast subject. It's a huge subject. No, I cannot do justice to this subject in a single course. So, we'll concentrate only on equilibrium aspect of this subject.
So,
A little bit of non-equilibrium after mid-sem.
so in other words, so how can we say that the system is in equilibrium so that we can apply these concepts?
So, if
Like-
your system has no time evolution, then they are in equilibrium.
No time.
No, for example, not time evolution, but if your system, if you calculate the quantities, ensemble average quantities, and these ensemble average quantities do not change with time, then your system is in equilibrium. But if they change with time, your system is not in equilibrium. When they don't change with time, only when the averages are taken over a distribution which is time independent and only a function of Hamiltonian. That is called equilibrium. Okay.
Got it, sir. Thank you.
Okay. This is very qualitative way of saying. So we'll stop here today, and stop recording.